Hello, everyone. Good morning or good afternoon, depends where you are joining us from. And welcome to our today's Quanser webinar. My name is Zuzana Fabushewa, and together with my colleagues Paul Karam, Director of Engineering, Peter Martin, Senior RD Manager of Academic Applications, and Tuvishan Rajagolasingham, Global Product Specialist, we will be your hosts and webinar moderators today.
Thank you, Susanna, and thank you, everybody. Thank you for joining us once again. We've been very excited to present a whole flurry of webinars over the last few months while everyone is finding their new normal and finding their working from home and being able to join us and connect digitally. So thank you again for coming. And what we're hoping to show you today is really a continuation of all the efforts we've been doing for the last few months, especially where a lot of our customers, a majority of our customers have come to us and asking us to work with them to help them take everything they've done with in working with Quanser, be it for their educational courses or for their research labs, and really working with us on how can we take those experiences for both the students and the researchers and deliver them in a remote fashion. How do we allow them to continue to work with Quanser, but in a remotely, where physical interactions with products are impossible. So I want to start this presentation with just to remind everyone, or for those of you who aren't as familiar with Quanser and our technology, our approach, why were we able to pivot fairly quickly and release a digital set of solutions that really complement and go really well with our physical product. So many of you who have worked with Quanser, or for those of you who are familiar with Quanser, we're very well known for our hardware. That's what we do. It's what our philosophy is, really bringing meaningful hands-on approaches to education and research as much as possible. Our philosophy with our hardware is that it's completely targeted for the academic market. So there is no black boxes. Everything's accessible. Everything is overly instrumented. Everything has a model and a mathematical representation based on many techniques and governing dynamics and equations of motion. And we make sure that hardware is repeatable, and that especially on the undergraduate level, you have the ability to have the same performance, the same repeatability, unit over unit, and over time when you interact with a Quanser solution. What we've also done alongside that hardware is completed the experience by a product called Quark. And really, Quark at a high level allows you to take a MATLAB Simulink user environment, this very sophisticated engineering workflow using MATLAB and Simulink, and take a Simulink diagram and actually target it on hardware. That's been a big part of our full offering for many years. And I think that's been a big part of the draw to Quanser, is the fact that from the lecture into Simulink, there's a very seamless step. And then from Simulink to our hardware via Quark, we make it extremely seamless as well. So that full workflow really works well, so that you can take the students from the theory in the lecture and through Simulink and onto our hardware in the lab. So those are the two things that we've been very well known for. Over and above that, our solutions always come with a wealth of curriculum, a wealth of examples and content, where you can use as is, or you can modify to really suit your needs as the instructor and your staff, to see what are the concepts or what is the experience you actually want to deliver to the students. So you can base it on our curriculum, but because we are based on the MATLAB Simulink environment, predominantly based on the MATLAB Simulink environment, really we are open architecture. And what we mean by that is, your imagination is your limit. Anything is possible because we give you the full access to the low-level I/O, and you can treat it as you will. And so you can base your curriculum off our curriculum, or you can completely do it on yourself. Some other assets that we've had, the two on the bottom, that we really brought to life when we were able to react to the market with when the pandemic hit, with a lot of our customers trying to finish their courses in the spring and now talking with us about the fall term and the uncertainty about how do you do everything online. And so some more assets that we have is we've had the ability to um, to provide knowledge and interactions via mobile applications. We've had an application called Experience Controls available on iOS and Android for over a year now, with over 6,000 users. The feedback has been resoundingly positive. It's a very accessible way to interact with a lot of the introductory control systems concepts. And to go right beside that, we've been experimenting a lot with the Unreal gaming and physics engine and how we've been utilizing that to bring some of our existing physical products into the virtual realm. And that's where we're going to really focus on in this webinar. I'm going to show you some demos. Hopefully you find them engaging. And I want the message I would love for everyone to take away is, Quanser has been providing really impactful experiences on the physical solutions that we've delivered to you for over 30 years. We are now taking those exact same solutions, the exact same experiences and workflows, and simply virtualizing it. So instead of a product showing up in a box, now the product shows up on your screen. And obviously the two play really well together. We fully expect that eventually, once we get through this pandemic, people and students and researchers will go back into the lab and physically touch the equipment. We still believe that is the best experience to provide engineers, in their undergraduate education or in their research aspirations. But also with this new technology that I want to show you is how the two can really play well together. So it's not an or, but an and putting the two together is truly impactful and really enabling students and researchers to further explore on their own time as well. All right. So really what we're going to be talking about today is the Quanser Interactive Labs solution. And then really that is Quanser Interactive Labs is a delivery mechanism where instead of getting a physical Quanser product delivered to you and showing up on your desk, you have a virtual Quanser product that shows up on your screen, where everything else is exactly the same. So it's the exact same workflow, it's the exact same curriculum, it's the exact same experiences we expect your students to have through this interaction, be it on the physical lab or at home, on this virtual lab. So virtual and physical, we see the full solution still being exactly the same. So in terms of, if we focus on control systems for a second now, like I mentioned before, we've released this product or this a free application called Experience Controls. Really, we saw that as a fairly progressive, accessible, modern textbook that's available, meet the students where they are. They can have it, in their back pocket on their phones or in their tablets. It's a very easy way for them to refresh some controls concepts. And because it's an application, it has a lot of interactions built into it. So you can actually see what happens when you move certain gains around or change dynamics or parameters of a system, and just see the other elements that come to life, as opposed to printed static images or charts on a textbook. So definitely, I'd say that if you haven't had a chance to check that out, please go ahead and download Experience Controls. You can just type it into either store and you'll be able to see it. An extension to Experience Controls is a product that we've talked about in the last few webinars, is a product that we call QLabs Controls. And QLabs Controls is a great way to really merge the experience of Experience Controls, and QLabs Controls delivers the lab exercises and the lab elements that really complement Experience Controls well. And then finally, I'm going to jump into a live demo right now to really show you, what we are talking about today. So the virtual versions or the virtual delivery of our physical plants. And I'm going to start with a classic, the Quanser Cube Servo 2. That is our introductory control system solution. And then we'll start with that. It's accessible because it is, it's a great way to really highlight the fact that a DC servo motor, when you look at the voltage to speed, is a great way to is a great example of what is a first order transfer function. Even that concept alone is quite powerful when after you described it in the lecture and brought it into the lab. So I'm just going to pause the presentation for a second, and I'm going to bring up a Simulink diagram here, and I'm going to first show you how this would work if we were sitting in front of each other and then I had a physical cube there as well. So I'm turning on my webcam. Hopefully, oh, there it is. All right. So this is my physical cube that you see right on my desk here. And with what I've been doing in this demo for over over 15 years now, well, has been fairly unchanged. And hopefully what you can get from this simple demo is really what is Quanser's typical experience? What do we expect people to do? Both introductory, when you have a student first come and interact with our solutions, all the way to research. I know this is a simple first order model, first order system when it comes to voltage to speed, and is a fairly easy product. But once you start adding things onto it, for example, a pendulum model, now this becomes more than just a education product. This is now a full-blown open architecture research product. And if you are interested, you can go out on our website, and we have over 2,000 research papers targeted there that show different research that's happened on our products for many years. So it isn't just for education. It's a great way to get students hands-on education, but also a great way to extend that into research. All right. So the demo that I typically do when I have the physical cube is I'll start with a transfer function. I think that's always a good way to start for any control system, especially for those of you who live and breathe control systems in your careers. It all starts with a transfer function. And I just happen to know that our transfer function of the cube is that. And what I'll do is I'll excite the physical cube and my simple model. I'm going to save that. And I'm going to select build. And so our typical workflow, again, it's based on MATLAB and Simulink. It's an open architecture. I just showed you one element of that by simply wiring it up as I wanted. And that's really what we mean by open architecture. It's fully instrumented. So even the cube, for example, here has the position, speed, and current measurements that come out of the device, and you drive it with a voltage. And what I just did there was generate the underlying C code behind that, so that using code generation from Simulink, and I'm just going to run that model right now. All right, so hopefully you can, in your video, you see that it's spinning around, and I'm my model is the blue, and my transfer function is the blue, and the physical cube, if I stop it right now, is that yellow. So that yellow is the plot of my speed, and you can see it's this simple transfer function captures a decent portion of the dynamics, but obviously doesn't capture some other things that are happening inside the cube clearly. And if I go into a more linear range at a higher voltage, then you can see the linear dynamics truly are dominant, and that's what better describe it in that voltage level right now. All right. So with that, I'll usually stop, and what I'll do is I'll delete this transfer function, and then basically get going with the physical cube and show how easy it is to take this physical cube block, and then based on the inputs and outputs, design feedback control systems to do one thing or another. But instead of doing that today, I'm actually going to open up something else. And so I will open up, excuse the mess on my MATLAB. So I will open up basically a very similar model, but except now, instead of me talking to my physical cube that you see on my desk, I'm going to be talking to the virtual cube. And that's what we really want to talk about today, is we are releasing now these virtual products, the virtual examples of our products through this Quanser Interactive Labs mechanism. And so for all intents and purposes, The only difference is that I've replaced the physical cube with the virtual cube. The whole experience, all the curriculum, all the MATLAB Simulink workflow stays the same. And I'll just do the very same demo that I just did now. So I'll drop in the transfer function again. So I will turn off the webcam. All right, so going back here. So this is the same demo, except now I'm simply targeting the virtual cube instead of the physical cube. We've done a really a good job, and we were trying to do an even better job as we start releasing all of these assets and these products in making sure that the virtual representation of our products present a hardware-centric approach to that model, meaning it's not just a simple transfer function. This is a nonlinear, high-fidelity, dynamic rendering of the physics and the equations of motion of every single product, not just the cube, but all of our other products that I'm going to be showing you today. And so we truly believe that this is a great way to still provide a hardware-centric approach. I will show you that even our low-level device driver calls call hardware access, for example, encoders. So I'm receiving a quantized signal of the encoders that would be the same type of signal that I would receive from the physical cube. If there's any analog devices that I'm sensing, there's a noise band that's proportional to what you see in the physical realization. We've modeled all the different components within the system down to the drive electronics and all the nonlinearities, including gravity, friction, and so on. So this is a lot more than a simple simulation. This is really capturing the true essence of the physical product and delivering it to you virtually. And so you can see very similar to what I showed on my physical cube. My transfer function is the same, obviously, but my virtual cube is performing in a similar fashion to the physical cube. It's not capturing some of the underlying nonlinear dynamics in this model. And then if I go back to a higher excitation level, then just like my physical cube did, my virtual cube is now performing a lot. It resembles a lot more that simple transfer function that we see over here. All right, so I'll go back to 1 volt, and I'll stop that. So that's just a great way that I typically try to demonstrate, our philosophy really at Quanser, where we want that seamless flow from the lecture. So this transfer function for me is where you as professors truly shine. You've worked really hard in explaining all the mathematics that are behind how do you take a concept like a model, a first order model or DC servo motor, and how do you derive the equations of motion that govern its dynamics via and capture that via transfer function. So and that's why I will start here to show that this is a great way to really emphasize that concept. And then once you have that, you can do a lot based on that model. There's tons of model-based design techniques that I'm sure you'll be showing to your students as well. But after that, I want to show really rapid controls prototyping, how easy we find it to use both our virtual and physical systems. So with that, let's just create a control system here. So I'm just going to zoom out a little bit, and now I want to command the position. So instead of looking at the speed, I want to command the position. So what I'm going to do is put in a summation block. And now instead of this being an excitation voltage, this will be my reference signal in radians. So I'm just going to plot that as well. And then I'm going to compare where I want it to go to where I am. So I'm just going to hook up the position sensor there. And then simply for this first example, I'll just take that error signal and feed it directly into the voltage. Let's see what happens there.
While that's building, hi everyone, I just wanted to mention one side note, which is the open architecture that Paul talked about with the actual hardware. That's the same open architecture here. So as much as Paul mentioned, the virtual plant doesn't necessarily resemble the mathematics, because the real hardware, as you saw, doesn't necessarily always represent the linearized mathematical representation. If you dive under the hood of both, you can see actual encoder signals, you can see actual voltage commands with saturation, and you can actually, it's basically the same open architecture on both sides as well. So it's not just a representative velocity or representative command, it's the same sensors and the same actuation with the same high fidelity models on both cases also, which is, so you can dive deep and see everything you'd like to see as well.
Yeah, that's a really great point, Peter. And you know what I'm hoping to show you here is when I go into that block, this is the exact same block that I had for my physical cube as well. So we initialize the device and then we do a write and a read, and that's basically the same paradigm to access all our hardware. And that's the same paradigm I'm using to even access the virtual hardware. So the signals coming out, this is an analog signal coming out. This is an encoder signal coming out. This is a digital speed signal coming out. So all of these are actually, you know, true to their form in the sense that now I can take this exact same diagram and simply tell inside here in my initialized block for it to point to the virtual or the physical. All I have to do is make one switch here, and then the model will target either the virtual or physical. So with that, you saw I did a very quick closed loop control system. This is a proportional feedback control system, and it's kind of getting there. It's got a bit of overshoot that you can see, and you know, it's really an underdamped response, but for more all intents and purposes, it's getting to where I want to go, just going there a little overshooting there. So what I'll do, as I'm sure all of you know, is where's the derivative term, and that's what will, if I add that in, that should help things along. So I'm just going to add a few legs to this control system now. So I will drop in a derivative term. Then I will sum 2 up. All right. And so here's my proportional leg summed up. Here is my derivative leg summed up. And this is probably a bit too high. And I'll run this again. And so hopefully what you're seeing with this is just how easy it is to really implement any algorithm you want. I mean, this is very simple, you know, PD controller that I've implemented here, but really like I said earlier, because we're using the full-blown MATLAB and Simulink workflow, the sophisticated engineering workflow, anything that's available in Simulink is truly available to you to implement on both the virtual and physical offerings from Quanser. So you can see right now I've done PD, and it's getting better. The overshoot's definitely gone, but it's, you know, a little sluggish in its performance. So I'm just going to up my proportional gain there. I've reintroduced that overshoot, and I'll up my derivative slightly, so I still get that responsiveness while really truly reducing that overshoot. So I'd say this is a pretty good control system, and it only took me a few minutes to go from, you know, validating the model of my system, and then, you know, had I basically used that model to help me derive these or get to these gains that best you know, are deployed to get this type of response on my controller. So hopefully what, you know, a big takeaway there is that we've done our utmost to make sure that the virtual experience resembles the physical experience for all intents and purposes, all the way down to the device driver calls that happen at the lowest level interface. And then, you know, over and above that, that workflow, that open architecture, sophisticated engineering workflow of leveraging MATLAB and Simulink, everything being instrumented, everything being visible to you on the screen, still is near and dear to Quanser, and it's still relevant and a big part of the what we provide, a big part of the student experience when you use even our virtual products as well. So with that, I will hand the presentation over to my colleague, Peter.
Hey, everyone. Thanks again for joining us today. And thanks for bearing with me while I interjected into Paul's presentation. So what I'm going to talk about for this first part of my demonstration is going to be the flip side to what Paul was showing you. So that, as you could see, was the experience of having a virtual piece of hardware, as Paul said, that behaves as close as we can possibly get to actual hardware. Obviously, it's never going to be the same, and we're a hardware company, so we know the value of having a real hardware physical experience. But at the same time, all the dynamics and the behavior of the system that's essential to learning about control and exploring a controls environment when it comes to hardware, we've replicated as closely as we can. And at the same time, you have that flexibility of MATLAB Simulink, and hopefully later on this year, other development environments where you can create your controllers or create your logic or your machine learning algorithms or anything else you want to take on around that piece of virtual hardware. And so can your students, which is the other big exciting option that's available when you have virtual hardware, is the ability for everyone to be able to leverage that hardware and have their own physical systems or virtualized on their desktop at home. But what I'm going to show you here is an example of, as I said, to a certain extent, the flip side of what Paul showed you, which is here, what I'm doing is opening up another one of our virtual products. This is the Quanser ARM, or the Q ARM. And in this case, I'm running the off-the-shelf controllers we would typically use with the Q ARM. And what I wanted to talk about with this demonstration was that for 30 years, we've been building up our collection of curriculum, courseware, teaching materials, example models, all sorts of resources to be able to use our hardware products in controls and an academic environment, whether it's for research or for teaching. And all of that material is available off the shelf to use with these virtual products. As Paul sort of alluded to with the changes that he was talking about to this block here, very minimal changes need to be made to existing Simulink models to be able to have them work with the virtual hardware instead of the physical hardware. And so in this case, this is an example of an off-the-shelf model for teaching robotics. The over 40 Simulink models we just released a few months ago for our CubeServo 2 platform that cover everything from the very basics of control systems all the way through to advanced applications, stability, and then getting into even more aspects of digital control and even some examples of nonlinear control and things like that. All of those can be run on the virtual products with very minimal changes necessary. And that really opens up a wealth of material that can complement these platforms. And on that note, in terms of the virtual lab experiences themselves, these virtual products that we're going to be showing you today, as we said, they're instrumented dynamically accurate. They're measured and controlled using MATLAB Simulink, the same as our other physical systems would be, and hopefully, as I said, later this year, other development environments we're working to complement the examples and the material that we have available. They can be used to enrich your lectures, but also your activities in traditional labs. We really believe that post-COVID, work from home and learn from home, these products will still offer a hugely valuable experience for students to be able to work with these systems, to be able to interact with their own versions of physical hardware at home, in their dorm rooms, or in the labs at the university, to really be able to experiment and really be able to address some of the challenges of delivering physical labs, like large class sizes, limited lab space, scheduling, students who have to journey long distances to get to and from universities. All of those can be eased having these virtual plants available. And then, as I said, they're compatible with standard curriculum resources, and the system that you use to be able to manage the access to these platforms, to be able to add your students to and give them access to these systems, is very straightforward. It's all managed using a cloud management system that's very intuitive to be able to give them that experience. But what this does is it really, as I said, builds up this complement of material, where what we're able to offer is really the only complete solution for distance and blended controls education and controls research, where you have the ability to augment your lectures. Like I said, you have the ability to do, to a certain extent, remote visualized activities, to be able to combine it with distance learning, combine it with offline learning. We have, as Paul mentioned, our complete textbook reference material that has hundreds and hundreds of instructor resources, just dozens and dozens of PowerPoint slides and sample questions and interactive examples for students to work with to really understand the basics of control systems and how it's used in industry, how it's used in different fields of research, so that they can really get a feel for how controls works before they implement their own controllers, in this case in MATLAB Simulink. We have that open concept exploration for students that they can do anytime, to a certain extent anywhere, if we start to leverage, as Paul mentioned, the QLabs Controls platform, where they have the cross-platform experience of using their phones, their laptops, Mac OS, as well as Windows. They have that ability to really use these control systems and learn about them anywhere they are. And then finally, the MATLAB Simulink aspect of being able to use that to be able to create your own controllers, and also to be able to give students the ability to really understand MATLAB Simulink, which for a lot of controls courses is one of the main outcomes, one of the really key things that students need to understand and be familiar with to be able to be successful later on in their careers and their academic careers if they so choose. So really, as I said, just to sum up, these experiments are a complete solution. They can be applied to introductory and advanced control systems courses, aerospace courses, manipulator robotics, and it's the same Quanser physical hardware experience that you've been using and your students have been using for over 30 years, but now virtualized. Now the ability for every student to have a robot, every student to have a servo, and to work with it and really understand how control systems comes to life when it's applied to these hardware and physical systems. So what I'm going to do now is slightly abruptly change pace. And I'm going to show you a little bit of what the experience is for instructors, what your experience is, as I alluded to, managing access to the system. This is one of the things that's new, one of the things that a lot of you would not be familiar with if you'd used Quanser hardware before, because obviously our physical systems aren't managed using a cloud platform. But we've spent the last 6 or 7 years building a large foundation of software support on the cloud, and also through our mobile platforms, to be able to deliver content seamlessly to students and instructors. And we've leveraged that legacy and that foundation that we built up to be able to deliver this product seamlessly and very easily. And so I'll just flip to my browser here, and I'll really quickly show you exactly what that experience is like. So behind the scenes, what I would have done as an administrator is create what we call an academic session. So create a scheduled time where you would and your students would have access to the platform. That would be obviously something that would be a part of the subscription that you would have as part of what you would have purchased for this platform that my colleague Vivashan will talk about a little bit later. But basically, you would have received an email, and that email would have detailed the steps you would need to take to be able to activate and use your subscription. And what I'm going to do now is log in as if I have received that email. Actually, not log in, register. I know what I'm doing. So in this case, the first step is to register. Everybody needs to register, whether you're a student or an instructor or the administrator for a session. Everybody has to register first, so we know who you are. We can attach you to the right content, to the right subscription. I'll just set a password. And I can set a username, and this is optional. Set a country, which is also optional. And then that's basically it. We have obviously privacy policies that are very rigorous to make sure that you and your students' information is protected. All that we ever gather is an email address and a password. That's the only information we have to gather. So there's not a lot of critical, sensitive information that we're holding on to. We try to hold on to as little as we possibly can, but that information is very closely protected. We have a lot of GDPR requirements that we adhere to, as well as legal requirements to make sure that everything is safe and nothing is going to be broadcast or used by third parties or things like that. And then we have obviously an agreement as part of GDPR if you're interested in being contacted about new products and features and things like that. But in this case, I'll just register, and I'll get a confirmation here sent to my email to make sure that it is actually my email address. This behavior will slightly change. We've been having some complications with our email provider, which has basically meant that sometimes these emails don't go through. So we're gonna, in the next couple of months, remove this requirement to be validated. It will still get a validation email, but it won't be required. But then here we are. I'm now in the academic portal. Welcome to the academic portal. And as you can see here, I have the session that an administrator has set up for me. In this case, it's a demo session that I've created for myself, but it would look very much like this. It would say your name, the institution that you're with, the product that you'd purchased, the number of seats that you have available for your students. Typically, that would be about 300 seats. And then obviously the start and end date for that session. And then if you just click on there, you have access to this very intuitive interface where you can add your students. You can drag, you can write your email addresses, you can use a text file, however you'd like to add your students to this session. You can just put their email addresses here. And then once you're done and you hit add users, they're ready. As soon as they register, whether it's on the Windows client, or if you happen to be using the QLabs Controls platform that we mentioned, you could also register using the mobile app. Then immediately they will see the content. They'll need to do no other steps to be able to access and use the platform exactly like Paul showed you. As you can see, if I open it up now that I've registered, I can open up the Windows client here, and if I log in, there's my content, and I'm ready to go. So it's a very intuitive and easy platform. And obviously there's other capabilities we'll be talking about in the next few months that we're going to be rolling out, things like being able to do instructor analytics to see how your students are using the platform, what they're interacting with, things like that. And also some other features that we've been discussing. But basically in the essence, what needs to be done to be able to manage your session, it's a very easy, intuitive process, and all the download links for all of the applications are here too. So everything is ready for you. And with that, I'm going to pass it back to Paul, who will talk a little bit more about potential research applications of this platform.
All right, thank you, Peter. All right. Okay, so just switching a little bit of gears, I just want to show you a snippet of some capabilities of this platform. Again, I think the one major takeaway, if there's one thing we definitely want you as our colleagues and customers to think about leaving this webinar, is what we provided here within our virtual product line is the exact same Quanser solution that you've grown with and worked with in the past. Simply the delivery mechanism is different. So instead of actually physically shipping you a product, we are giving you access to the virtual product so that it shows up on your screen instead of on your desk. And really what I want to show you here is, like I said earlier, how we believe in the long run, once the world is through this pandemic, how we can leverage both of these assets, both the physical and the virtual, to even provide a more engaging experience for students and researchers. So for example, right now, like all of us are finding new ways to work, this is what I've been working on as well. I don't just provide webinars, I'm actually one of the developers as well in the company. And so I'm working on a lane keeping algorithm for our new research platform, the self-driving car research studio. And so very simple algorithm, I've been tweaking it for some time. And this is it performed on my my setup. And so excuse the mess in my basement, but that's the space that I work with now. And this is the car trying its best, and probably not doing as good a job as it could, to stay on the yellow line while looking ahead. And so I'm trying to push its speed here and trying to predict curvatures in my lanes or in my path ahead of me and trying to compensate for that beforehand. So that's really the algorithm that I've developed. But I wanted to show you here is one of the assets that we've released right now is our virtual QBot. And the QBot is a great entry into mobile robotics, and it has a great curriculum complement that you can be deployed on that. But what you're seeing here is that exact same algorithm that I had developed and deployed on the Q car, on the physical car. I've taken that exact same algorithm and deployed it on the virtual QBot. And so what I want you to take away from this is how seamless to go from the virtual to the physical and back, and having that rhythm and having that iteration, we truly believe is quite powerful, not just for teaching but for research. If you fast forward a bit into the future, regardless of once everyone comes back into the physical lab, there's still limitations. You still have to have access to the lab. You have to share the equipment with colleagues and so on. Where with this virtual approach, there is no limitation on access. It is truly scalable. It's fully rendered and active on your own desktop, on the student or the researcher's desktop at home, wherever they happen to be. And so you have access, a lot more. It's a lot more accessible than the physical product ever was, because of the fact that you have to share it and be at that location with it as well. So there's a lot of advantages of having these two together. Like Peter said, our philosophy is a hands-on approach to engineering education and research. We will always believe that, and we always believe that engineering is an applied science, and you need to have access to physical devices as part of that education and research. But this is a modern and sophisticated workflow. I mean, when students graduate and go into industry, this is part of that workflow. You want to understand the system. You want to develop and deploy algorithms on simulations, and this is really just a much more high fidelity virtualization, which is an extension of a simulation before you go back to the physical, and having the ability to go back and forth, because we're using the same blocks, the same interfaces, we truly believe will lend itself to that workflow as well. All right, and finally, I want to introduce to all of you my colleague Thuvashan, and Thuvashan's been with Quanser for a few years now, and is really taking a new role of being the global specialist when it comes to all of our virtual offerings. And I'll pass the mic and the screen over to Thuvashan.
Thanks, Paul. So I'd like to take you guys through and give you guys a bit of an insight in terms of what's available now. One moment. Beautiful. So you guys should be able to see my screen now. Perfect. On our website, what we have available right now is the actual virtual solutions that we're super excited to go live today, where you'll be able to access the information on the individual basis. So for instance, if you wanted to take a look at the QLabs virtual arm, on our website, there's additional material information for you to read up on. There's the ability for you to request a free trial or request a quote if you're interested. And we'll jump into what that looks like shortly. But everything lives and breathes on our website. We point everyone here. We have white papers to download, as well as additional material that you can view for your reading pleasure. With that, let me jump back into the presentation. So as Paul and Peter were mentioning, there's a lot of advantages the moment you go into the virtual realm. Things become easy to use, scalable, low effort in terms of actually setting up with regards to IT infrastructure. So Quanser's extremely excited to be paving a path for the future of the way engineering education is going to be taught, both on the research side as well as the teaching side in terms of their use. And today what we have for you guys is 4 virtual solutions. It's the suite of our QLabs Virtual CubeServo 2, the Quanser Aero, the QBot 2E, and the QArm. All have their different flavors and tastes and applications use, but effectively the positioning for these are for you to take these virtualized solutions and to have the exact same experience as you would if you were dealing with the real hardware. So imagine a student that's going through an undergraduate mechatronics degree. They may have to go into a lab and only get access to use a robotic manipulator as a group. And even then, the challenges were limited based on time and availability of the actual hardware. Now what we're trying to do and what we envision as a future capability is each of these students would be able to rapidly prototype, test, and deploy their algorithms in a virtual environment, come to the actual lab setting, and then have that exact one-to-one experience with the real hardware. And that's the true power behind the hardware-centric virtualization approach, where you're able to download your own test results. There's no risk of damaging the actual physical hardware, and there's zero setup time needed, which makes it very easy and intuitive from a user standpoint when correlating what they're actually learning or research that's currently being applied from a testing standpoint. So the best part about these solutions is they do come, as Peter had mentioned, with instructor and student courseware, and they're all fully compatible with MATLAB and Simulink. With regards to the actual procurement, it's a license of 12 months. It's a subscription license for 12 months, and each vary in terms of their hours of lab exercises and curriculum topics offered. And for your specific applications, what I would definitely recommend is either try the free trial on our website or request a quote, get in touch with a Quanser representative or a partner of Quanser, and we'd love to explore more in terms of your future needs to discuss how we can best help you. And the overlying statement that I'd love to mention is with these solutions, we do have options for multi-year support, as well as bundling of different solutions for an interdisciplinary approach. For example, if you're looking at utilizing the Cube Servo, as well as the Qbot 2E and the QArm, as just an example. So with that being said, we are a feedback company, and we constantly get the pulse of what our customers need, and they tell us exactly what they're using our solutions for and what they envision their future of teaching and research to be. So with that, these platforms are specifically designed for bring your own device use, meaning students have access to MATLAB Simulink on their PC, or a research professor could have their own software personally on their own laptop at home or even in the lab. But primarily, there's two underlying principles that need to be there from a system and requirement standpoint. The individual needs to have Windows 10 64-bit or better. Right now, that's currently what's offered as top of the line, as well as MATLAB Simulink 2019A or later. The underlying principle there is because we are using a Unreal physics engine, which is effectively a 3D gaming engine, it really requires some a decent capable processor and graphics card that's able to support these applications. But when you're going through these immersive, high-fidelity, engaging, interactive virtual experiences, it truly is intuitive and a wonder to work with. With that being said, as I mentioned, we are envisioning a future where there is an entire product suite of Quanser solutions that have been virtualized for use and exploration. And we're excited to announce that 4 more solutions are coming down the pipeline. We're expecting these to come in the next semester. And these will be based on our rotary servo solution, so the SRVO2 rotary base unit, with add-on modules of the FlexLink, the ball and beam system, so classical controls, and then the coupled tanks. So please keep an eye out. If you have any feedback or thoughts, please get in touch with our team, and we'd love to work with you to better support. But we envision a future where there is a direct one-to-one experience when utilizing either our physical solutions or our virtual, creating a more accessible world where you're able to enhance your teaching and research efforts. So with that, I'm going to open up the floor to questions. Perhaps, Paul, would you love to maybe mediate, and you can either direct it to Peter and myself or take it yourself.
Excellent. Well, thank you, Thubishan, and thank you everyone for attending today. Like Thubishan said, we have just under 10 minutes left in the presentation, so we'd love to open up the floor. Hopefully, what you saw resonated with you, and you can see something that you can make use of in the upcoming fall term. For those of you who do have terms in the fall, so please reach out to us. You visit us on our website. Like Thubishan said, we have free trials available for everything we're showing you today. So please, sign up and reach out to us, and we'd be more than happy to help. So with that, there's a ton of questions, which is fantastic, and I'll start with the first one. So the first question was, hello, are the interactive labs available under the LabVIEW environment? And so I'll field that one for now, and that's a fantastic question. And really, what we've done in our approach to taking everything we've done physically for all these years and simply delivering them to you virtually is using that same paradigm. So our products have always been open architecture, meaning that at the lowest level, you have device driver APIs that you can use to access the hardware. So that is the same paradigm that we've used for the virtual products as well. So at the lowest level, there is low-level C and C++ APIs available to access the virtual labs. LabVIEW is one of those software environments that we are considering fully documenting. We already have a lot of documentation based around LabVIEW. What you'll see in the shorter term is obviously right now we're documenting everything and really making sure the experience is as straightforward as possible with the MATLAB and Simulink environment. We will shortly after that be releasing more examples around the Python and C and C++ environments, and those can be used for example, to be imported into LabVIEW. We are still looking into, how much documentation we can put around LabVIEW, and the functionality is available because it is open architecture. So if you are interested in that, please reach out to us and we can have that discussion. All right, so a question for Peter here. Are the high fidelity equations of motion, their implementation in the virtual systems available, open, or documented?
That's a great question. Actually, I'm going to use this also to leverage a couple of other questions too. I've been sneaking ahead in the pipeline in the list here. So basically what I'll say, which is what we've said a couple of times today, but also applies to some of these questions, is when the virtual plants themselves, what we make available with these virtual plants is the same experience as the hardware. So in terms of the features and the specifications, you could just as easily go to the website for the real physical systems and learn what the number of encoder counts is, what the maximum speed of the motors are, things like that, masses and moments of inertia. They're all exactly the same as the physical systems, but also that extends beyond the physical systems to the experience of using them. So if we don't necessarily have the ability for you to open and change or modify our physical systems, and in this case, it's the same experience where we've done weeks and weeks, if not months, if not years of development effort to really accurately model, represent, and run in real time the dynamic models of these systems, and therefore we're not necessarily making them modifiable just as you wouldn't modify the physical system. But again, with the experience that Paul showed you and alluded to with our open architecture approach, everything surrounding that physical system is very open. You can interface to it in a number of different ways. You can change the sensor signals. You can modify behavior. We're working on being able to disturb the systems by tapping them or moving them around or things like that. You can reconfigure them the same way as you normally would with our systems in terms of adding or removing disk loads, adding or removing pendulums. For some of our other systems, you'll be able to lock different axes and things like that. So it's the same behavior as the physical system, but again, the downside to that is we don't necessarily open up the physical system just like we wouldn't the real physical system. And also, there were a couple of questions around being able to have different types of assessment questions in the environment, things like whether or not it's running on the cloud, things like that. Again, it's the same physical experience. So the same approach that you might take with your physical lab, you can take with these systems, where the assessment is the same assessment you'd use for the physical systems. We do have a slightly augmented experience where you'll have the availability to see when students are using the experience and how long they used it for. So you'll have some insight into whether or not you're getting the value for your investment in terms of how students are using the platform. But we don't have built-in assessment or things like that, just like with our physical systems, we don't have built-in assessment features or things like that. And then also, these models, as I said, their performance that we're guaranteeing and the communication between the virtual world and the dynamic models and things like that, all of that is driven by our decades of work in real-time dynamics and real-time control on Windows. And so that's all being handled behind the scenes in a high-speed real-time thread that we're running in the background that spawned when those virtual systems are opened. And so to answer the question about whether they're running on the cloud, they're running on your Windows machine in real time and communicating back and forth between the Simulink environment and the Unreal environment. So it's basically kind of a high-speed traffic cop that's making sure that the dynamic model that sits in between the two sends the right dynamic response to Unreal and also sends a representation of that right dynamic response back to Simulink to make sure that that experience is as seamless as it would be with the real hardware. But to guarantee that it has to run on a Windows machine, and as Duvishan said, a Windows machine that has a fair bit of heft to be able to handle that. I hope that answered 3 or 4 questions.
Thank you, Peter. And this is there's a similar question here, but I'll throw it to for Thuvishan. So Thuvishan, there's a question: what is the subscription model? Is it per student, per class, and an order of magnitude of the cost involved?
Beautiful. So with Quanser being a global company, each situation can vary. We have partners across the globe to support us. With regards to the actual structure, effectively, we work with each institution to meet their needs. So if there are varying class sizes that expand, where some of our institutions, as an example, will have class sizes in the order of magnitude of plus 300. And then we have institutions that only have class sizes at a size of only 5 per seat. So we really work on a case-by-case basis, and that's really why we request people to get in touch with our team, and it's more of a consultative approach. So what I would recommend in that case, especially for the pricing that varies, please get in touch with the Quanser rep. Myself most likely will be that individual, and we can really work with your team to define a pricing in a budget range that works for you and your institution.
All right. Thank you. Thuvishan, was one other question, and I'll take a few here as well. Can the students have control over the virtual lab, or only the instructor can have the control and the students just view?
This is meant to, so maybe to generally answer, the solution is meant to support a one-to-many access. So it's purpose-built for students and instructors to have access on their own independent machines or their own personal electronic devices. And effectively, everyone could be, we envision a future where the instructor has the actual physical hardware in a lecture lab setting, and they're going through the actual material on both the hardware and the virtual environment. And each student will have the virtual environment open up on their laptop, and they can be following along or testing and rapidly prototyping independently. So the purpose and goal would be to have everyone equipped with the virtualized hardware and able to explore at their own independent pace, which really promotes individualized learning and the rapid prototyping capabilities to the nth degree, being able to explore on that level.
Yeah, forgive me for jumping in again. But exactly as Thuvishan said, the one thing I wanted to emphasize is, especially when it comes to the robotics products, for me with a robotics background, it's really exciting for me to be able to with this platform talk to our colleagues and customers about the ability to give every student their own manipulator system and every student their own mobile robot. Because obviously, whenever it comes to hardware for lab experiences, it's very difficult to have enough hardware for all the students you would have in a class. But for robotics, like having a manipulator system for every student where every student can use it as much as they want and really explore it and really do exciting and fun things with it, it's a super unique experience and something I'm really excited to be able to offer.
All right, I'll just field a few here that I've sort of put together in terms of the theme, and thank you for all of you who sent in those questions. Thank you all of you who've attended it, and we'll make this webinar available, and we'll definitely, if we haven't answered your question, we'll make sure somebody from the team responds to you with an answer as well. I think just to remember, what we've done is there is no cloud elements other than the subscription activation itself. Everything else is happening on the Windows PC. So it is the expectation is that your students, if you're interested in using the virtual products, the students are in the have a Windows PC. They install MATLAB and Simulink on that PC, and then the Quanser virtual labs work on that same PC as well. So that's just to make sure everyone's aware. So that's why we mean by scalable, because it's every PC is self-contained and running this full experience on its own. So you can have many of these. All your students have their own unique experience in that sense. And yeah, when it comes to modeling, I think we touched on it a little bit, but we have made sure that we know our systems fairly in great detail and in depth, and we've been modeling them for close to 30 years now. And so all of that expertise has been, taken and implemented within the virtual offering. So every component within the system, anything that affects the dynamics or the equations of motion or the behavior of the system has been implemented and considered. And through various elements, we are leveraging a physics engine. We are leveraging, obviously, high-fidelity dynamic equations of motion, nonlinear equations of motion as well. And we're doing a lot of system identification on our physical plants as well for those parameters that we don't have, given, the numbers for as well. So a lot of effort has been made to make sure that whatever we provide is as close to the physical as possible, being all the while being delivered virtually.
Thank you, Paul. Thanks, Pete and Tuvishan, for the presentation. And of course, thanks everyone for joining us today. And we are looking forward to seeing you at one of our future webinars. Thank you all for joining us today.